I would like to start the second lecture of statistics class. Last lecture, I introduced the type of hypothesis and property of z-scores. Z-score can be calculated like this, and using z-scores, we test the hypothesis. In the basic statistics, very basics, then we assume the standard normal distribution. Standard normal distribution is here. The most mean should be within the -2 standard deviation, 2 + 2 standard deviation. Here, within this area, the proportion is 95. This is 95% percentage. So the if there is your sample's value is here, your sample's value is here, that is the out of the 95%. So that is, we can say there is the statistically significant difference. In 5% level. That is the content of the previous lectures. And chapter 2, we introduced the mean, standard deviation, variance, and the sample and population's difference. This is the real-world model, and a good engineer will try to build a best model. The model best fits the situation of interest based on the data available and predict things about the real world. This is the best fit model, this is moderate fit, and this is poor fit. We can say that it is important when we fit a statistical model to a set of data that this model fits the data well. And if our model is poor, then the predictions will also be poor. So we should create like this, the good fit model, better model, and show the real world situations. Then we use the data set, but we can only use the sample. That is only the limited part of population. Population and sample is totally different. Population is the collection of units to which we want to generalize a set of findings or a statistical model. Population is target, for example, the worldwide dataset, world people's characteristics, how they think, or what the behavior of the all over the world, or whole in Japan, or whole in US, and so on. But this is usually unobservable. We cannot gather the data from all of the people. So in many cases, we only use the sample, the limited sample, a smaller collection of units from the population used to determine truth about the population, part of population, and available information. This is observable dataset. Sample is enclosed by red line, and the red region here this is the sample, and this is only a small part of population. But our goal is population. We want to estimate the population's value. All over the world, the average and for example, what is the average? For example, what is the average income all over the world, and like that. But we can only ask some limited per people. What is your income? Then we only use sample, but we need to predict the population's value. That is parameter. Our goal is here, outcome equals model plus errors. A simple statistical model. In statistics, we fit models to our data. The mean is a hypothetical value, and the mean is sample statistical value. This is the important fact. It means that this is the statistical model or the hypothetical value, and sample mean is not always same as the population's mean. If the sample is very biased, then the sample do not show the population's characteristics. Then it is called biased, and the estimation result is not true. That is very problematic for statistical estimations. The mean can be written here. The mean is the sum of all scores divided by the number of scores. The mean is also the value from which the scores deviate least. And the mean example is here. This is almost the same as the previous lectures. We add them up, and the sample is 1, 3, 4, 3, 2, and we sum these, then we get 13, and divided by the sample size, then we get 2.6. This is the mean. The measuring the fit of the model is here. The mean is a model of what happens in the real world, the typical score. It is not a perfect representation of the data. How can we assess how well the mean represents reality? This is a perfect fit case. The rating is all 5, or the individual rating is all of them rate 5, then the mean is perfectly same as the all result. But in many cases there is the deviations. Deviations can be calculated here. The sum values minus the mean of them, then that is the deviations. This is the error for each one. Deviations can be calculated by taking each square and subtracting the mean from it, like this. For example, this is the 1, 2, 3, 3, 4. 1, 2, 3, 3, 4. This is our data set, and calculate mean, then we get 2.6. 2.6 is this blue line, and there is the differences. This is the deviation. For example, one sample, the value is 1, but mean equal 2.6, so the difference is 1.6. And another sample, the difference is 0.6, 0.4, and so on. So if we add all of the errors, then we calculate the goodness of fit, sum of squared errors. Errors are, some error is minus and some error is plus, so we need to square the deviations. And total is here, total is 5.20. This is the sum of squared errors. Some are positive and others negative. Then this is the sum of the errors. This is the important value because this shows the deviations, sum of deviations, sum of the errors of and between the value and our mean, our statistical value and samples difference. That means, and we can calculate variance using this sum of squared errors. Variance can be calculated here. This 5.2 is here. Sum of squared deviation is 5.2 and 5.2 is here. This 4 is sample size minus 1. So in this case, in our case, the sample size is 5. 1, 2, 2, 3, 4 is our sample. So the sample size is 5. Then divided by 5 minus 1 equals 4. And the squared deviation is 5.2. Then divided by 4, we can get the 1.3. This is the variance. And also we calculate the standard deviation. Standard deviation is the square root of variance. So we can get the square root here. This is the variance, and square root of variance equals 1.02. Standard deviation is used a lot these days instead of at the two standard deviation, or some researcher says at the two standard deviation or at the three standard deviations, there is the differences, or the two standard deviations level differences. This is the standard normal distribution, and this is the standard deviation part. We get in this case, standard deviation is 1.02. So minus 1 equals minus 0.02. If we use n and minus 1.02, and this is plus 1.02 plus 2.04 minus 2.04, because we can calculate the specific standard deviations. So within here, and 25%, and outside of here 5% level, statistically significant. Significant difference. Like this. So calculating this value is very important for us. When using a normal distribution for estimation, we always discuss it with the standard deviation. And the sum of squares variance and standard deviation represent some kind of same thing. The fit of the mean to the data, the variability in the data, and error, and how well the mean represents the observed data. This is left-hand side, Left-hand side, this figure shows a large standard deviation case. This is a small standard deviation case. This is volume of tail is large and volume of tails are small. This is a small standard deviation, so it's sharp shape, and this is a broad. So this is more easy to find the statistical differences because if we use the standard normal distribution, the value of sigma, value of standard deviation is small in this figure, but large in this figure. Sometimes we say it's efficient, it's more efficient. Okay, so the next I would like to explain samples and populations again. Sample is mean and SD describe only the mean and SD describe only the sample from which they were calculated. And mean and SD are intended to describe the entire population. This is target, and we want to say the population differences, but we only can use the sample as data. So we predict or we estimate population by using sample. Next figure is the population and the sample relationship. Population is here. Many kind of people. There are many kind of people. Someone laugh and someone is angry. I'm not sure, but there is the population. And we get data set from the populations. I want to use the pen. For example, this is a sample 1. This is a sample 2. Each circle is sample. For example, this is sample 3, sample 4, 5, 6, blah blah blah. And this figure illustrates the process of taking samples from our populations. We get these samples from the populations. Population is only one because the whole people. And this illustrates sampling variation. Samples will vary because they contain different members of the population. This is a very important point. We can only use the samples, but we do not know which is our samples. For example, by chance sample average is 2, and by chance sample average is 5, 3, 4, 1. But the population, our target is the same, but the sample's statistics is changeable by chance. Then this is very difficult to accurately estimate the population values. So we estimate by using the normal distribution. We assume the normal distribution of the sample mean. Then we can estimate the populations. We can test the hypothesis. diagram below is a histogram obtained by collecting multiple sample averages. This is the multiple sample averages. If there is a lot of sample set, and this is the distribution of averages. Each sample has different averages, different means, and if we draw the histogram by using a lot of samples, by using a lot of averages of many samples, then we can write like this. And this shape should be normal distribution. If we collect the samples at random from population, if a sample is randomly collected from sample, then this distribution should be always normal distribution. So we assume that this distribution and our sample is, we are not perfectly sure our sample is the representative, our sample represents the population, but for example, the 95% of the sample means should be within here. So if the value is within here, we cannot say there is a statistical differences. But if the value is out of here, out of the green area, then we can say there is a statistical differences at 5% level or 1% level, like that. The important thing is that our target is population, and we can only use the samples. And the sample means distribution should be normal distribution if we can get the sample at random from populations. So the randomly, how to say, we get the sample at random is very important, and also in that case we can assume the distribution. So the normal distributions characteristics is very helpful for us. A sampling distribution is simply the frequency distribution of sample means from the same populations. In theory, you need to imagine that we are taking hundreds of or thousands of samples to construct a sampling distributions. If the average of the sample means is the same value as the population mean, if we knew the accuracy of that average, we would know something about how likely it is that a given sample is representative of the population. Central limit theorem means that sample size gets large, then the sampling distribution should be the normal distribution. This is the central limit theorem, and based on this theorem, we can say these samples mean distribution is asymptotically same as the normal distribution. This is the standard deviation, and usually we need sample size should be large because the sample size gets large, then the sample distribution is a normal distribution. And some researcher says greater than 30 sample size, then that is enough large. But some part doubtful. If you write your paper that the 30 sample are sufficient, then today's academic research, this is not enough. Actually, I think this is not enough. So the sample size, for example, the 60 or 100 or more than 1000, that is if you have the 100 or some hundreds of samples, that is much better than the 30 or 60 samples. Central limit theorem definition is here. As n sample size becomes large, then the distribution of sample mean approaches a normal distribution. This is the central limit theorem, but it assumes that the random x1, x2, xn should be a random sample of size n. So random sampling is extremely important. If the random sampling is not guaranteed, then we cannot assume the normal distribution. Then we cannot test any hypothesis using this kind of the economic or statistical methods. And sample size is larger would be better. 30 is a bit too small. Also, I would like to introduce the confidence intervals. This is the Japanese quote Uzura, in Japanese Uzura. I'm not sure the Japanese quote, the bird's name. These days, within 2 standard deviations indicator is commonly used for these confidence intervals. And this is the point estimation and confidence intervals. Confidence intervals is here, and this circle point is the point estimate, the mean. I think this is the mean, and this is the 2 standard deviation intervals. And for example, the 46 sample number is 0 to 51, and 46 sample case. This sample is 95% range is here, and this is not include this value, then the don't contain the true value. In some cases, in some samples, do not contain the true value within the 95% interval. So if we gather a lot of samples, then there is some errors. But basically, the 95% intervals contains the true value. In this case, true value is 15. So the statistical estimation is not perfect, but this is the very, the useful or helpful to assess, to test the hypothesis. The fact that the confidence intervals overlap in this way tells us that these means could plausibly come from the same population. This is come from same population. Could plausibly come from. This is the important word, not perfectly. And if the confidence interval is different, do not overlap, then we use the 95% confidence intervals. Then this one and this one could be come from the different populations. Do not overlap, then that is different from the different populations. Within, then this can be, we may say the plausibly come from the same population, same. This is different. Test statistics is here. This is same as I said. If within here, within the 1.96, then that is the 25% of distributions proportion. So we cannot say there is a difference. But if out of 1.96, almost 2, out of -2, and lower than -2 or bigger than +2, then we would say there is a statistically difference in 5% level. And there is the one-sided and two-sided test. In general, two tails is better. One-sided means that only use the one side test. So in that case, we ignore the minus part, only check the plus part, only check the plus 1.96 standard deviation case. That is the one-sided test. But in many cases, two-side test is conducted today. Calculating confidence intervals is here. P is the probability value for the confidence interval. And in this case, the 0.025. The procedure that I have just described is fine when the sample size are large, but for small samples, the sampling distribution is not normal. It has the t distribution. If the sample size is large, then we can use the z distribution. Z distribution is normal distribution. But the sample size is small, then the t distribution is better. Most researchers use the t distribution. The t distribution is a family of the probability distributions that change shape as the sample size gets bigger. T-test means the statistical test using t distribution. Z-test means the statistical test using the z distribution. Both z and t distribution assume the random sampling. So if the random sampling is violated, then we cannot use such kind of test. Type 1 errors and type 2 errors I would like to explain. The null hypothesis, as I said, the null hypothesis is no effect, and hypothesis is there is the effect. Type 1 error is we believe that there is the effect, but there isn't. This is a type 1 error. Type 2 error is we believe that there is no effect, but there is effect. That is type 2 errors. We face with both type 1 error and type 2 error. So we need to consider which kind of errors can be emerged in your dataset or in your test. Sorry, I'll restart the statistical class. What does statistical significance tells us? The importance of an effect. This answer is no. The significance depends on the sample size. It is not only depends on the effect size, but also depends on the sample size. So if we have a lot of sample size, then we can get the statistical significance or statistical difference more easily. So it is always means the importance of the effect, and also the null hypothesis is true or not, then we can say no, it is not true. There is no effect. This is the null hypothesis. We can deny this argument by the test. But the statistical significance is not always means the size is big. Effect size discussion is here. Cohen shows some standard for the effect size. For example, in the case of 1% of the total variance is explained by one variable, then the variable's effect is small, and 9% then medium, 25% is large. This R means the correlation. So the R equals 0.5 correlation coefficient is the 0.5. Then the variance is 25%. It means 0.25. This is just a rule of thumb. So this effect is not guaranteed by other research domain. So please read the previous papers in your research domain and check what value is the big effect and what value is the small effect, you can say, if you want to mention about the effect is large or not. Next, we can introduce the statistical power. Statistical power is we can calculate that by using the R or specific software is G power. Also, even Excel can calculate the statistical power. We use the sample size and effect of size and the probability. The first one, the post hoc case, calculate the power of the test given that we have already conducted our experiment and we will have already selected a value of alpha, statistical significance level. We can estimate the effect size based on our sample, and we will know how many participants we used. If this value turns out to be 0.8, we can be confident that we achieved sufficient power to detect any effect. But in practice, it is more informative to report confidence intervals because this is not stable. And I recommend to check these statistics before conducting field survey. A priori case, we calculate the sample size necessary to achieve a given level of power, Given that we know the value of alpha and beta, we can use past research to estimate the size of effect that we would hope to detect in an experiment. Even if no one had previous research, then we can still estimate the likely effect size based on similar experiment. Before you conduct the field research, we check the previous research and the similar effect. Then we can get or we can guess the effect size. And we set the statistical significant level, for example 0.95 or 0 and 0.05. Then we can get the required sample size. We should calculate the required sample size in advance conducting the field research by using the software like the G⁻R and others. When the methodology is relatively simple, for example OLS or t-test or something, then you can use the G⁻and use the result as it is. But when the methodology is more complicated, for example the random parameter model or GM as a method, then please use the result as the maximum number required, and more larger sample size would be better. Okay, this is the chapter 2's contents, and homework is here. Please download R and R Studio before the next class. This is the homework. Just downloading is all. You can use the generative AI. You can use generative AI, so please ask. You can ask the ChatGPT or Claude or something how to download the R and R Studio and how to use them. From the next lecture, I introduce the R code and how to use the R for statistical analysis. Okay, that's all of chapter 2. Thank you very much for your listening.